All right, alkylation of the alpha proton. So we've been talking a good bit about chemistry now at the alpha proton, and we want to talk now. So what have we done up to this point? We've been talking about how we can, what have we done? I don't know. We've been talking about aldols and Claisen, right? And how we can make carbon-carbon bonds with that. This next section now I think is going to be somewhat intuitive. We're going to make the enolate, right? And you've seen that. That looks just like a nucleophile, right? So we've seen nucleophiles before. Well, the picture's down here. We've seen nucleophiles before come and displace a halide, right? So if we can make the enolate with LDA, which looks like this, bulky, strong base. Bulky meaning it's not going to be a nucleophile, right? Then we can, after we make the nucleophile, this is, don't forget, this is resonance stabilized, or else we would never get that, right? That's going to attack the alkyl group, which is exactly what you might expect. All right, the enolate attacks the alkyl halide via an SN2 reaction. You've seen this 100 times. Where's my marker? I need my marker. Where is it? Here it is. Via SN2 reaction. You've seen that 100 times. All right, so now when secondary or tertiary alkyl halides are used, the enolate can act as a base in an E2 reaction. Pause the video now and show what we mean by that. When secondary or tertiary alkyl halides are used, the enolate acts as a base. Draw that out. Pause the video now, draw that out, and show what does that do to the enolate. That's the question. What does it do to the enolate? So the aldol reaction also competes with the desired alkylation. So this we got from a couple sections ago. The aldol reaction also competes with the desired alkylation, so a strong base such as LDA has to be used. So a strong base such as LDA has to be used. And you remember from a couple sections ago the methods that we used to make sure that ways that we can control the aldol reaction. So regioselectivity is often an issue, and what we mean by that is if we've got two alpha carbons, here's an alpha carbon and here's an alpha carbon, where are we going to get our alkylation? And that's what the next couple slides are all about. All right, so suppose that we've got two alpha carbons. Here's one and here's one. This one's a secondary and this one's a tertiary, right? And they're not the same. So if we introduce LDA or some strong base, we're going to get both possibilities, right? Well, it turns out that the faster of the two, the base more readily abstracts that proton, right? Boom, it's gone. And so we have that enolate, okay? The less substituted. That's the kinetic. This is faster. All right? However, if this proton gets abstracted, this has the more stable intermediate. It's slower, but it's more stable, okay? So it's thermodynamically favored. Remember what is meant by kinetic and thermodynamic? Let's look at the next couple slides here. So first of all, faster is going to have a lower activation energy, right? But more stable, not in every case, but in this case, so this is going to be slower, right? Because it's got a higher activation energy, but even though it's slower, it still has a more stable intermediate. This isn't always the case, right? It's not that slower gives a more stable in the end, but in this case, when we're dealing with a reaction that has one product is going to be faster and one product is going to be more stable, the other one's going to be more stable, then we have to consider this issue. We've done this before. So for clarity, the kinetic and thermodynamic pathways are exaggerated, so these actual numbers are not given out here, so I'm not even sure why that comment's necessary. Explain the energy differences below using steric and stability arguments. That would be a good test question. We don't do a lot of free response essay questions, but it'll help you think through it if you pause the video now and think and address that. Explain the energy differences below using the steric and stability arguments. Give you a hint. I sort of already addressed him. All right, now LDA is a strong base, and at low temperatures, it's going to essentially be irreversible, right? And we did that. We looked at that in class. What is meant by irreversible in terms of an equilibrium? That's usually a reversible reaction, right? But if we change the energies, or if we fiddle with the energies enough, or the temperatures, which give accessible energies, then we can make it an irreversible reaction. We can essentially say, all right, we're going to push it so hard that way it's not going to go back. All right, so if we go cold with LDA, we're going to get the kinetic, right? In other words, not enough heat to overcome activation energy of the thermodynamic product, okay? Which would be the other side. Now, if we give it some heat, 25 degrees Celsius, roughly room temperature, then in that case, it is enough, and it will, and also we give it a base which is not quite as strong, then it will go to the thermodynamic product. Okay, now stop the video and practice with conceptual checkpoints 22.33. That's probably 23 and 24. I think it's 23 and 24. I think that's a mistake. All right. Okay, now the malonic ester synthesis. This is a new reaction. The malonic ester synthesis allows you to take some alkyl halide and tack on a carboxylic acid at the end of it. Oh, that's powerful. It allows us to take an alkyl halide and tack on a carboxylic acid. So we're adding two carbons, right, to this R. So first of all, we're going to take diethyl malonate. This has to be memorized. Diethyl malonate. And we're going to take a good strong base, which is not super bulky. Notice, by the way, that this base is the same as that, or rather this ethoxy group is the same as that base. So if we get transesterification, it's no problem, right? So we take some base and we abstract a proton and we make this, okay? Pause the video and draw the resonance structures. Pause the video and draw the resonance structures for that. How many are there? All right, so in the malonic ester synthesis, again, we take an alkyl halide and we add a carboxylic acid to it. Let's look at how this works. So first of all, we take our diethyl malonate, which we draw that out a few times, get used to it, okay? We deprotonate it. With what do we deprotonate it? Look at that base. There's my base. So we deprotonate it with ethoxide, sodium ethoxide probably, right? And after we get that, then we have a nice nucleophile and we do an SN2 reaction. Real simple. Nice. Okay? Now we have this. Well, this is not, let me go back a slide. That's not the same thing as this, right? So let's go back. How do we get that? Well, first of all, we're going to hydrolyze the esters. So we use acid and heat to make carboxylic acids now, right? And then we're going to decarboxylate. So after we decarboxylate, this is a mechanism which you haven't seen before. It looks kind of like the Diels-Alder, though. It looks a lot like the Diels-Alder, really. Okay, so we make a 6-membered ring, and then we switch partners. Okay, so after this, these electrons go up here and make a hydroxyl. These come over here, make a double bond. These come here and make a double bond. And so you see that I'm left with, see, there's my carbon dioxide. Carbon dioxide leaves, and I'm left with an enol. Really, it's an enediol, right? But this tautomerizes to make, and there's my new 2 carbons, and my new carboxylic acid. So why isn't a second carboxylic acid group removed? It would be excellent practice to stop the video and practice this decarboxylation, and then remove the second one and see what happens. Remove second carboxylic acid to prove it to yourself. Remove it and see what happens. Where's my marker? Okay. All right, so here's an example of the overall synthesis. We take sodium ethoxide in ethanol bath, of course, and we deprotonate that. After we deprotonate that, we first of all make that, right? And then this comes, bam, bam, and we hydrolyze and decarboxylate. Okay, and that's what we get. So we took what we essentially did was we took our benzyl bromide, right? Snip, snip, and we put on top of there this guy right here, right? You see it? There's what was my benzyl bromide. Okay, so go practice that and make up a question. See what you can make from it. You might also say, how can you make benzyl bromide? Right? That would be a good synthesis question. How do you take benzene and make that? Good question. Okay, now double alkylation can also be achieved, and we're just going to do it twice. So if we want to double alkylate, you want 2 of those on there. We can, where am I here? Man, I'm losing my marker today. Where is it? Just a minute here. There we are. We do it once, then we do it a second time, and then we hydrolyze and decarboxylate. Okay, so go practice with Skill Builder 22.5, and then we'll come back and we'll look at the acetoacetic ester. Okay, I'm going to assume you practiced with that. You just did Skill Builder 22.5, and the acetoacetic ester synthesis, very similar process. Very similar process. It's going to, though, instead of tacking on to the R, instead of tacking on a carboxylic acid, it tacks on a methyl ketone. All right, you see it? Okay, so we're going to do the same thing, except this time we don't have the diethyl malonate here. We've got acetoacetic, let's see, ethyl aceto. Just a minute here. What's the name of that stuff? I don't remember what the name of it is. I don't remember what the name of this is. So it looks like it's, oh, I don't know. The common name. Let's do the long name. One. It's going to be ethyl, right? And that's this part right here. And so it's going to be 1, 2, 3, 4. It really starts here, right? 1, 2, 3, 4. Butane. And if it's an ester, it's going to be butane 08, ethyl butanoate. So it's going to be 1, 2, 3 oxo. So it's going to be ethyl 3-oxo butanoate, but there's a common name for it which I just don't remember. It's like ethyl aceto acetate, something like that. All right. So, but you see, it looks almost identical to diethyl malonate, right? Diethyl malonate looks like this. Right? Looks almost identical to that. So we're going to use the same reaction conditions. Sodium ethoxide and ethanol, and then come in with some alkyl halide, which in this case we're going to use benzyl bromide, and then we're going to hydrolyze the ester, make it carboxylic acids, and decarboxylate. Okay, go practice with Skill Builder 22.6. Good luck.